see from the graph on my back. So just now when we mentioned about this equation, when you do the first part, actually there's some typo error, or there are some equation error that we put here. Because if you look at these steps to these steps, you are actually processing the A and not you are processing the T. So that's why from here to here, it should be 10A and not T. It should be 10A and not T. So there's a typo error there. So I move on. So this one is just the answer that I gave you just now. So make correction. So this actually, when I prepared the slides, there are some typo error. So correction, if you move from this step to here, the correction should be A times 10 minus A minus 0 equal to V minus 0. So this one 0. So this step should be 10A and not 10T. Just a correction. And so from these steps also make correction. V equal to 10A, not T. There's a typo error here. So correction, your V equal to 10A. So here also there's some missing information, because when at the time of 10 seconds, your acceleration is 10. So in this case, it's because we have a coincidence that our value of time and acceleration is the same. So that's why it's still able to save the question. But in the exam, if this time and acceleration is not same, then you will spot the error from here. So so T equal to 10, velocity 100, how to get 100? Luckily, we are saved by the same value, right? So correction now, when the T equal to 10 seconds, your acceleration is also 10. So just now we do correction, V equal to A10. So when we substitute, okay, when you substitute your V, how you get 100? V equal to A10, and you substitute your acceleration as 10. So 10 times 10, you get 100. So we still get the same magnitude, okay? So again, this is the typo error in the slides. I already make all the correction here on my slides. You will see this one when I distribute the slides later. Okay, just to remind everyone. Okay, I hope. Okay, thanks, Prem, for your question. Right. So take note. There are some typo error in my slides. It's not T, but it's a A. Right? It's a A, not T. Okay, let's move on. And again, yeah, this equation wrong already lah. That's why I put a line there. Okay, let's move on. The rest steps is correct. Okay. Let's look at a curve motion. A curve motion where we're given a name for curvilinear motion. Curvilinear. We have done with the linear motion, means move in a straight line. Now we're going to study what happens if the particles move in the circle, or move in the curve, not circle, move in the curve. Okay, again, we are now looking at curved path and not straight path. So again, just a reminder. When we study about a particle move in a curved path or curvilinear motion, our path normally will be in 3D or three-dimensional, meaning you have your X, Y, and Z. If you have a Cartesian plane, if not, then you need to define in the R, theta, and Z. So you have two kind of position system, but normally we'll use Cartesian, right? And we need to use vector analysis So this also fall under your advanced mathematics. There's one chapter we learn about vector. So you need to apply what you learn in your mathematics in this chapter or in this section. So vector analysis means when you have two vector, what happened to the resultant vector? Okay, but anyway, we will recall or refresh the concept of vector later on. And then for curvilinear chapter or section, there are three important keyword that we studied before this. We keep on continue using the same keyword: position, velocity, and acceleration. S, V, and A. So we continue to apply the concept of position, velocity, and acceleration. Okay, and the derivation of the equation that we'll use, I will give you Appendix B, where you can look at it later on. You can read. Appendix B more on the vector. What happens if you have two vector and you want to find resultant, the derivation steps for vector analysis, I will give you in Appendix B. I will upload in the Teams folder. Okay, later you can download this one and have a read if you need help on the vector analysis. Okay, it's just extra information for you. So the first one, because we have three important keyword here: position, velocity, and acceleration. So we look at the first one. How we define curvilinear motion position, the first one. So normally we'll define position like what we did in the straight line position. I will use the solid blue line to represent the position or the path that taken by the particles. Blue line represent path, and usually we'll use S to represent position. So let's say we have a red dot on the path, a curved path, right? On a curved path, then you have a red dot there, and this red dot move along the curve, right? So this move along the path. So we need to define position, velocity, and acceleration for that particle. So we need to know how and where is it this particle. Because from the position, then we can derive, from position we can derive velocity, and from velocity we can derive acceleration when we know the time frame or the change of time. Okay. First thing, path, position. So when you have a particle move from origin to one new location, we can define it in a function of t. That's why there's a bracket of t there, meaning the particle move from one location to another location. And since the path is in t function, or you will see a linear equation or a quadratic equation, s equal to t squared plus something, like what you see in the previous example, like just now. Okay, so the first thing is path function. The blue line you can define with the path function. If you have a linear function, y equal to ms plus c, then you get a straight line. If you have a linear equation, if you have a quadratic equation, then you have a smiley face or curvilinear, or you have a polynomial, then you also will have a curve motion. It depends. So we need to repolish how to plot linear graph, quadratic graph, and polynomial graph. Just flip back to your mathematics textbook. Let's say we have an origin of 0, because you know that all the circle, there is a locus there. There is a center of a circle. Okay, so we will see this one as a simple circle for this moment. So simple circle, you always have an origin. I label x with the label of O to represent origin. And you know that when you draw a circle, you will have radius, right? How you measure radius? Radius is the position from outer circle to the center of the circle. And in this case, we use the more familiar notation, which is r, which represent a radius of the circle, right? So r also in terms of t, you see bracket of t means it will change according to time. So from the red circle on the top to the below of circle, then the time will be changed. So we have two equations so far on the screen here, which is the path that you can define in the function, radius can be defined in function of time. Both change with time. Position change with time, you get velocity. Radius change with time, you can calculate the rate of change of the position, right, for curvilinear motion. Okay. Now, so far we talk about the basic definition. How do we find the position first? So stop me if you're not able to absorb the general definition. So we have talked about path, we talk about radius. So for curvilinear, it add one more dimension to define the position, which is the r, because curvilinear, you seen it as a circle. So circle have a origin, and the distance from origin to that position on the curve or on the circle, it give you the radius. Okay. So remind yourself, position is a vector. Vector have magnitude and direction. Okay, vector have magnitude and direction. So you need to again open your mathematics textbook, how to find magnitude of a vector, how to find direction of the vector. Means later you will see theta, you will see magnitude of the vector. Second one, once you have a position, then you need to consider displacement. Displacement means the change of position from one position to another position. So this one will be our reference of our position. Then from position, we can talk about displacement. Okay, so we have two positions here, origin and new position. Okay, we have two positions here, but since we have the change of position, we can talk about displacement. So let's say these red particles make movement from the top to bottom at an interval of time delta t. And just to remind you, triangular delta means a small, very, very small changes. Very, very small changes of time. So for displacement, we look at very small changes of time, and the particle move a small distance we denote as delta s along the curve. And in this case, let's say we are looking at particles and we use microscope to zoom in the positions of the particles. So let's say from the top to bottom, we have delta s, and the particle use delta t to travel from the top to bottom. Okay. Okay. So we have delta t, delta s. And you know that when you have a delta s and delta t, you can find velocity. Okay. And just to add on, for curvilinear or movement on the curve, you need to consider one more parameter, which is the radius. It is the radius to define the position of the particles that move in circle or in curve pattern. Okay, so you have change of position s, that what you learned in your linear motion previously. And when you come to curve path, you need to add one more parameter, which is the radius, the change of radius, which is the r, from here to here. So I will use r prime to denote the new radius position for the new position. I'll use r to represent the origin radius position from O to the S up there. And if you see r comma or r prime is the new radius measured from origin to the new position. Okay. And you know that on the far left there, I put a note there. Position is a vector. All right. Position is a vector. So when you have two vectors add together, you will get a resultant vector. Okay. So vector, you measure from origin to the location, you get an arrow pointing from O to the position, from O to the position, and the resultant of vector you always draw from the origin to the end position, correct? This is what you learn in vector. Vector, you always have the tail and the head. The tail always from the origin, the head always pointing to the last position. All right, start applying vector concept here. So you have the r, r prime, and delta r. We represent the red color arrow as your resultant vector, but it falls under position. Okay, now I slowly guide you through how we apply from this simple diagram, apply with the vector analysis, you're able to process curvilinear motion. Okay, all right. Right, so just a quick recap or quick revision. What is the difference between curvilinear motion and linear motion or straight path? Are you able to answer that? All right, just ask yourself, what is the difference between straight line movement and a curvilinear motion or a particle move in the curve path? What have been added in the formula? Okay, on this diagram, you know that R is added compared to the linear. Linear, you only focus on S, right? Okay, we'll move on. So by looking combined vector principle from this one, you know that vector, how you calculate vector, R prime equal R plus delta R. What does it mean? When you draw vector from O to up there and continue the journey from up there to below, it becomes the combination of vector you put in one side. And normally how you find the resultant of vector is always from, you only interested when you plot vector. On the left hand side, the resultant vector, you always consider, you only look at the origin and the end position. So that's why on the left hand side, we are using R prime. This equation will be changed if you use different vector. Right? This is just, this equation only apply to this scenario. Huh? But the concept of vector still there. Again, I remind you, this equation only apply to this scenario. So what happened if in the test or final exam, I change the motion of the particles? You might not able to use this one, but you have to think using vector analysis principle. You look at what is before and after, right? But the concept will be how you draw this vector equation. You always start from follow the motion. The right hand side always the motion sequence. For example, how you move from you look at the whole vector diagram, and then you study how the arrow pointing. There will be two arrow pointing that give you the sequence of motion, and then one arrow will give you the end result from the beginning to the end. So in this case, as you can see from this diagram, R prime is the one that gives you the end results. R plus delta R will give you the sequence of vector motion in this equation. Okay, I hope you can see how you derive from this diagram to here. Give you 10 seconds to digest. How are you able to, from this diagram alone, from the orange color arrow and the red arrow itself, by using vector analysis, are you able to understand why we can write in this way? Okay. Stop me if you need more time to digest. Pranesh, are you there? Pranesh? Pranesh Vino?
Yes, it is.
Okay. Are you able to understand what is this one?
Yes, sir, getting it.
Okay, good. Okay, I highlight on the slides just to remind you that it is important. Move on. So this is a vector concept. However, when we talk about displacement is delta R, is a change of position. We use delta R to define displacement. We use this equation, rearrange. You put your R from right hand side to left hand side. That's why you get R prime minus R. And again, all these are vector. R prime, R, they are vector. So you still need to hold on the vector understanding in here. So you can see that you are actually subtracting two vector here. You're taking the end vector and the beginning vector to get the displacement. Okay, so from here, you arrive at here. And remind yourself, what is the definition of displacement? We use delta R. And delta R is a vector subtraction. You take the end minus the beginning. Okay. All right. So second equation. If you understand this one, you're able to arrive at here. Okay. Apologize for all the shown. So I will copy the vector diagram for the next slides, and I remove all the information on the screen. So okay, ignore this one. So just now we already defined how to find displacement delta R. Okay, delta R is you take the R prime minus R, and this one is a vector form. So we have done with position, displacement. Now we use information of position and displacement to find velocity. Now, previously when we learned about linear motion, we have average velocity. VAVG means average velocity. If you're hardworking, you can write the whole average word here, right? But your lecturer is a bit lazy, so I write V sub AVG equal change of position divided by time. In this case, we no longer talk about a straight line, we talk about curve. So for curve displacement, we use delta R, the change of radius vector. So average velocity equal to displacement. In this case, for curve path, we use delta R instead of delta S. So equal to average velocity. A new equation for today when we talk about curvilinear. Okay. We also learn, when we learn about average, we learn about instantaneous, where we can change the delta, triangular delta, to D symbol. Okay. Again, triangular delta is a very, very small changes, but we can change these small changes to something that we can measure. So we put in the limit of time there to change the triangular delta to D delta. Again, this is a side note. So we can use this operation to change the triangular to D delta. So basically, okay, all right. Okay. So the next one will be, we will need to equal ds and dr. As you know that when you learn about a circle or section of a curve, all right, as you know that when you have a very, very small changes of angle between 2 points on a circle, you actually can equal your s versus r, right? When you learn about section of the curve, when you learn about trigonometry, then you know that your s, you can calculate in radian, s equal to r theta when you have a very, very small curve. That's why in this case, we try to apply trigonometry equation where we equal the displacement and the position. Okay. So from here, if we have a very small changes on a curve, we can straight away use ds over dt equal to dr over dt. But however, if you have a long curve, then you can only use this equation. Okay. This is a side note for you. All right, we move on. Okay. Okay, now again, this is velocity. Velocity is a vector. Vector has direction and magnitude. So just to recall, the magnitude of a velocity, we call it speed. Let me see if I put it somewhere. Okay. So I draw an arrow. I draw an arrow there. A green arrow was added. So a green arrow, I label as V, a vector there. So there's a V vector. So to find, so this one is just an equal. I think I missed out the thing. Okay. So this is just to explain why suddenly your dr and ds can be the same. Okay. Right. All right. Now from the previous diagram, we define the position, we derive the path, s, r, delta r, and now on these slides we define the v, it is vector, and this vector is tangent to the curve. Okay, when you learn about trigonometry and we learn about curve, you should know what is tangent to the curve, right? So let's say you have a circle. What I mean by tangent to the curve means it's only touching on one point on the curve, and is something like that. You can draw the tangent by using this arrow, something like that. Okay, so just take note on that. For curvilinear motion, your velocity vector is a tangent on a curve. Just take note on that. And for engineering dynamics, there's a difference between speed and velocity. When you talk about speed, it means magnitude of your velocity. Okay. move on 1 or 2 more slides, then you call it a day. All right. Now, we talk about acceleration. All right. So just now we talk about velocity, and we move on to acceleration. So let's say we continue to use the same curve, same path. So when you talk about acceleration, what is the definition of acceleration? Let me ask Sivendra. Sivendra, are you there? Calling Sivendra. Calling Sivendra Krishnamurti.
Yes, I can hear you, sir.
Okay. What do you understand about acceleration? How do you define acceleration?
The rate of velocity which changes with time, sir.
Okay, so it means you have changes in velocity. So very good. Okay, so at the time t, you have velocity vector with the green arrow. And as these particles change velocity along the curve, when you move from one location to another point at the change of delta t, you'll get the second velocity as it moves along the curve. And we assume that this particle is getting a higher and higher velocity. We represent, when we draw vector, you know that the length of the vector represent magnitude, right? So from this diagram, you know that these particles is accelerate, because you from the vector length itself, you know that this position and this position, at this position, the velocity is increasing. And once you have a change of velocity, you know that this particle is accelerating. And in this case, we use v prime as the second velocity, or the new velocity at the new position. All right. So again, you know that velocity is a vector. There's a change of vector. You can put them into a vector form, where you know that a new vector v prime equal to the original vector times the change of vector delta v. Right? So this is just a normal logic conclusion, where how you get the new velocity, there must be changes of velocity. So you take velocity times the delta v. So again, just now we talked about average velocity. Now we talk about average acceleration. Average acceleration equal delta v divided by delta t, which is a change of velocity divided by t. You get average velocity. And to get instantaneous acceleration, we will use limitation of time equals 0. We can change the triangular delta to d. Okay, so I just rearrange my equation. I pull my v to the left hand side. I get v prime minus v equal to delta v. I put them into a vector diagram. I put them because vector, you can draw. What is vector again? Vector is direction and magnitude. Direction and magnitude. You can put these two vectors together at one point, and you can draw the magnitude and direction, magnitude and direction. You can draw the resultant vector here. Okay. So again, this is just a change of the velocity vector here. So I pull the data from the curve here, this one and this one, and I put them together as a vector diagram. All this you can read lah. Okay. I label as O prime, means I pull these two diagrams and put somewhere somewhere on the sheet of paper, and I put it as origin of these two vector. Okay, V, I follow the direction and magnitude. I just copy the direction, and I pull the same data from here, and you can draw the vector diagram, right? So basically, there's one more magnitude here. Okay. Yeah. Okay. So when I move the two vector to a new sheet of paper, and both of them join on the origin, because these two vector, they move in a curvature motion. So I can plot, just to maintain the velocity, I can add one curvature on the arrowhead here. That's why I add a dot line here. This dot line is a hodograph, or something that you use to you create to analyze vector that move in the curve. You can say it's an imaginary curve on for vector analysis. Okay, so this imaginary curve, or we call it hodograph, will be different from the actual path. This dot curve is based on O prime. It's just based on O prime, or where is this O prime? O prime is just a location that you choose any place on your sheet of paper, and you just copy the vector. You just put the two vector together that start with the origin. And to make these two vector relevant that move in the curve path, you add the curve between the arrowhead, and you can do a curve along the V to V prime. We call it hodograph. Okay, so don't confuse with the dash curve and the path. The solid line path and the hodograph, it will be different. It's a different thing. Although they share the same curve form. Yeah, today you learn a few more things, where we learn how to export the vector onto a new dimension or new sheet of paper. You learn a new word called hodograph. Hodograph is for vector analysis that start with the origin prime or a new origin. Okay. And just now I mentioned you can draw a vector from here to here. It's for vector analysis. Yellow arrow, just to know that this one join this one to complete the vector analysis. We can know that this yellow arrow is delta V, the change of velocity from here to here. Okay, so we will move away the diagram on the left, and we focus on hodograph and this equation. So average velocity, this direction, this equation, and instantaneous acceleration, we use limitation. We change the delta into d. A equal to dv dt. That's what you learned in your linear motion just now, previous class. Okay. So when you define instantaneous acceleration, dv over dt, what does it mean? Again, we are looking at hodograph. Okay, we are looking at hodograph and not the path that we've seen just now. Just take note on that. When we talk about instantaneous acceleration, we talk about hodograph, that two vector join together at one imaginary center. I label as O prime, and this O prime contribute to the curve of your hodograph. And when we talk about instantaneous, it means this acceleration will be tangent, a tangent to your hodograph or tangent to your imaginary curve. So don't confuse with the solid line I showed you just now. We are talking about on hodograph. So when you plot graph or plot the vector or illustrate the vector on your answer, when you talk about velocity, from the imaginary center, you draw the curve of your hodograph. Acceleration, we talk about instantaneous acceleration, means you're talking about motion on the hodograph with its tangent on the curve. Okay, so something new for today. And yeah, so this is just a side note lah. Just in case you forget in your revision, I put a side note here. Okay. Then recall what we learned just now. V equal to dr dt. dr is a displacement. So we try to link dr in this equation. So you know that when you put your dv over dt again means you double differentiate the velocity, means you can write in double r d square r divided by dt square, means you double differentiate the velocity. So you have two forms of acceleration. You can use the dv over dt, or if the equation gives you in terms of r or displacement, then you can use the second equation. Okay, to find acceleration, normally you look at the question. If the velocity is equation, then you use the dv dt. If the question starts with displacement delta r or r equal to one long equation, then you use the second form of equation to calculate a, and this one you need double differentiation, or the skill in differentiation. You differentiate two times the r equation, then you get acceleration. Okay, so this just also recall from your previous mathematics class. Okay. Now back to a solid line. Right. So a path with velocity just now. This is what you see in the real case. Hodograph is what you imagine, right? So I add in an arrow just now. Before I explain about the arrow, you try to imagine how a particle moves on a path. Does the particle continue to move outside the curve? No, right? So when we talk about a curvilinear motion, the particle will always stay on a curved path. You ask yourself, what actually contributes to this kind of behavior? There must be something pulling the particle inside towards the center of this curve, right? If there's no pulling force, how come these particles can stay on this path? Cannot, right? They must. If there's no pulling force, then this particle will move in the linear motion. However, when we study a curvilinear motion, let's say we know that these particles move in a curved path, there must be something that always pulling this particle towards center, right? Towards center, if this particle moves in a curve, right? So what is the force that pull the particle towards the center of the curve? Right? This yellow arrow is actually the acceleration that we find just now. Okay? So something new, open up your mind this morning. They actually, for curvilinear motion, the acceleration have a special characteristics when we talk about curved path. The acceleration always pointing inside of a curve. Right? So imagine if you have another curve with inverted curve. Just to help you sketch the direction of acceleration, is always follow the curvature, concave of your path. Let's say your curve is like that, right? How you draw a circle? Go inside, right? So what happens if your curve is like this? Sorry. Okay. What happens if your curve is like this? I hope you can illustrate lah. So what happens if your curve is like this? It's going inside, right? So your acceleration will be pointing inside the curve. So this is how you draw the acceleration vector direction. Okay, so just take note on that. Ask yourself, are you able to guess or estimate the direction of acceleration on the curve path? Look at the curve. Ask yourself, where is the center of the curve? It's inside, right? So the acceleration will be pointing inside. If the curve is another direction, then it's pointing to the center of the curve. Always looking at the curvature of the curve. All right. So if you understand what we talk about today, then we can call it a day, right? So this is just a side note for you, right? That I explain why the direction of A is pointing inside and what contribute to the particle that always stay on the curve path. Okay, this one you can read from here. And yeah, I highlight one more time, the vector of your velocity always tangent to the path. Okay, when we learn about curvilinear, this will be the thing that you always need to remind yourself when you solve question in the curve path. Direction, because we talk about vector. Vector, you have to know the direction and the magnitude. So magnitude, no problem. Magnitude, you can use equation to solve. But direction, you need to observe where is how the particle move, and when you plot the motion, you have to know how to draw this one. Always tangent to the curve, and how you draw A is always pointing towards the center of your curve. Okay, I think we stop here and see you tomorrow for next class. All right, let me stop the recording.